Does the Van der Graaf generator exert a force on this pitfall over here and keep it pushed away even though there's no contact being made? Or, go to the next slide. Does the Van der Graaf generator alter the space around it, and this altered space exerts the force on the negatively charged pitfall? Does the Van der Graaf alter the space around it, and the altered space exerts the force on the pitfall? So it's basically like this. There's two ways of thinking about it. This way over here, the Van der Graaf generator somehow or another puts a little tiny force, pushes that pitfall away, even though it's not even touching it. No contact is being made. Or the other way of thinking about it, the Van der Graaf generator somehow alters the space around it. And the space, after it gets like tweaked somehow, changed somehow, altered somehow, it's the space itself that puts the force on the little hanging pitfall. Well, next slide, you can think about it either way. No one really knows. However, there's a lot of benefits to thinking about it the second way. There's benefits to thinking about it as some kind of alteration of the space around it, and this space does the pushing on the pitfall. This is a man-made concept. Some physicists don't buy into this. Other physicists use this all the time. It's such a model, it's such a useful thing that it becomes something real to them. So we're going to learn about this alteration of the space here. So how is the space around the charged Van der Graaf altered? How is it actually tweaked? No one really knows. No one really knows how the space around the Van der Graaf is tweaked. It doesn't even matter if there's air or if it's an empty space vacuum. Even if all the air was sucked out of this room, and it was an empty vacuum, this Van der Graaf generator would still push that pitfall away. Is space itself somehow altered, somehow tweaked? No one really knows for sure. How do we know the space is altered at all? Well, by the fact that the pith ball is being held up there. Somehow or another, that space right there is different than if the Van der Graaf disappeared. With the Van der Graaf there, and that pith ball just kind of being pushed up like that, we know that there's got to be something going on there. Okay, so how do we know the space is altered at all? From the pith ball. We think it's altered because the pith ball is pushed without anything touching it. Physicists say that the space around the Van der Graaf generator contains an invisible electric force field. Keyword being invisible. You can't see it. And it's called an electric force field. And that it's the electric force field that exerts the force on the charged pith ball. So again, this is where we're going with this, folks. Okay. Instead of thinking of this Van der Graaf generator directly pushing on that pith ball like that, we're thinking about it this way. We're thinking of the Van der Graaf generator creating some kind of force field around it. And it's the force field that exerts the force on the charged particle. What does the electric force field look like? It's invisible. You can't see it. When you charge up that Van der Graaf generator, you can't tell if there's a force field around it by looking at it. Sometimes I like to just charge it up and leave it by the door. People don't know any better, they walk right near it. Zap. Well, if you can't see them, how can we visualize this invisible field? How can the electric field be visualized if it's invisible? And this is what we do, folks. By drawing arrows called electric field lines. That show what a tiny imaginary positive charge would do. If placed at that particular location. How can the electric field be visualized if it is invisible? By drawing arrows called electric field lines that show what a tiny imaginary positive charge would do. Now, sometimes it's a lot to say, tiny imaginary positive charge, so I give you a little acronym here. Tiny imaginary positive charge, a tipsy. Whoa! Tipsy. We place a tipsy. Tiny imaginary positive charge. Now, up until now, we have thought of the positive charges as being the protons locked up in the nucleus. And that's the truth. That's where the positive charges are found. And the protons cannot jump from atom to atom to atom. So in all the experiments we've done up till now, the protons are the positive charges and they are not free to move. But this is a pretend thing that we're doing. We're using a pretend positive charge, and we're pretending that it is free to move. So let's get started. Let's say we have this positive charge, or I'm sorry, this negatively charged globe, yes? And we want to visualize the invisible electric field around this. We pretend to place a tiny imaginary positive charge in the space around the charged object. And we ask ourselves, how would that tiny imaginary free to move positive charge respond to this negatively charged object over here? And what would it do? It would attract, and it would go towards it like this. If I place the tiny imaginary free to move positive charge over there, and then I thought, geez, how would that sucker respond to the negatively charged Van der Graaf generator? Well, I draw an electric field line showing the path it would take. Now, normally, folks, we don't even draw the tiny imaginary free to move positive charge. We just pretend to place it there in our minds. So if I pretend to place it right here, yes, I know it would respond by moving right in this way. If I pretend to put a tiny imaginary free to move positive charge right here, it would move in this way. If I put it right here, how would it respond? It would move in this way. These green arrows, called electric field lines, help us visualize the invisible electric field. By definition, by agreement, the field lines always show what a tiny imaginary positive charge would do. Another thing that the field lines indicate is the overall strength of the field, yes? If you look over here, do you see how like the field lines here and here are kind of like relatively close, the spacing between them, yes? Well, where the field lines are like close to each other, that's where the field is strong. And then if you go further away from the negatively charged Van der Graaf generator globe, say out here, notice the field lines. They're getting farther apart, yes? And you see how when the spacing gets farther apart? Well, that indicates to us, oh, that's where the electric field is weaker. Now, sometimes only the field lines are shown, and the object that actually produces the electric field is not shown, like on that next slide. In this slide here, you have the electric field shown, but not shown is the object that created the electric field, yes? In your mind, you might think about like, well, what object might be there that would create that electric field? But you do enough of these, you start to know enough about these electric field lines that you don't even care what the object is that created it. You can answer all your questions just by studying the electric field lines. Let's look at an example. Let's go to the next one. Which arrow indicates the direction of the force that would act on a proton if it was a free to move proton, not locked up in a nucleus of an atom? Which arrow indicates the direction of the force that would act on the proton placed in the field? Again, you're not even shown any other objects. You're just shown the proton placed in those electric field lines. What do you think there, Ashley? Okay, here's the thing. The field lines, these field lines, they always show the direction that a positively charged particle would go. Since they always show the direction that a positively charged particle would go, they show the direction that a tipsy would go, yes? Then guess what the answer is? 4. So the answer is 4. If you go to the next page, again, the electric field lines are shown, but the object that created the electric field is not shown. And then the question goes on to say, hey, if an electron was placed in this invisible electric field like this, which arrow indicates the direction of the force that would act on the electron placed in the field? Miguel?
2.
Yes, it is choice 2. Okay. By definition, the field lines always show what a positive charge would do, yes? So if a positive charge would be flaring out like this, flying this way, well, we know that a negative charge would experience a force in the opposite direction. What object is probably over here creating this force field in the first place? A positive charge. Are you positive?
Yes.
Right, you're neutral. Oh, yes.
Is it possible for it to be one?
No. No. Later on, when we study another type of force called a magnetic force, we're going to be mapping out another type of invisible force field called a magnetic force field. And then it will be either 1 or 3. It's perpendicular to the field lines. But with electric field lines, it's either with the field lines or against the field lines. Okay, another typical question. Electric field line shown, charged object that created the electric field is not shown. At which point is the electric field shown the strongest? 1, 2, 3, or 4? Steven? And the correct answer is 1. Because, look, the lines right here and right there, they're the closest together. Over here at 4, they're spaced out the farthest. And then 2 and 3 are, in the middle there. Sometimes people get fooled and they choose 3 because it's on the line. That doesn't mean anything. You have to look at the spacing between the lines. So the answer is 1. Whoa. Okay. Yes, as I was saying, the electric field lines surrounding the charged particles can be visualized with the electric field lines, even though they're invisible. So here we have 2 objects. The 2 objects are anchored down. Sometimes people think that the arrows that we draw are showing how these objects would move. These objects are stationary objects, anchored down. They're not going anywhere. But they create some kind of aura around them, some kind of alteration. They create an electric force field. we want to be able to visualize this invisible field. So what you need to do in your mind, pretend to place a tiny imaginary positive charge and then draw an arrow showing how that tiny imaginary positive charge will move. Hold on one second. Whose birthday is it? Whose birthday? How old are you, Zach? 17?
Say it louder so they can hear you.
Physics reading mix.
That's good
Okay. Back to education mode here, folks. We want to visualize the invisible here, yes? So, pretend to place that tiny imaginary positive charge in the various spots and draw lines in the areas all around both charges here. Okay? Draw the electric field lines. Show me what you got. Show me the money. You're not going to draw the little positive sign. You just pretend in your mind to place it. No. Don't draw what I'm drawing. You're drawing the real deal. You're drawing the real deal. Huh? You got it going, but the lines are continuous from one object to another. It's not like two separate fields, you know? If you put a little Tipsy right here, yes? How would that sucker respond? Well, at first it would be moving away from the positive, yes? But then what would it do? Curve. Yes?
Physics reading mix.
That positive one right there? This one here is not the Tipsy. This one here is a second object in its own right. Okay?
Physics reading mix.
So we have two complete objects there. And we're drawing the electric. So that's a very good question. This here is not the Tipsy. This here is another object in its own right. You know what I'm saying? Like we could just draw the field around that object alone. So if I put the Tipsy right here, how would it respond? It would go away. If I put it here, it would go away. If I put it here, it would probably go up. Put it here, it would go up, go down. If I put it over here, it would go down. If I put a Tipsy here, it would go in like this. So it looks something like that. Yes, you can put one straight across. Yes?
Is there like a certain angle from the positive object where the particle won't reach the other field, so it won't curve in?
Probably like straight up.
Is there a measure of how the reach will be here?
Eventually, we're going to actually measure it, and we're going to actually give particular points, particular number values. So eventually, we're going to say, hey, how strong is the field right there? And it's 57 units strong. And then maybe out here, it's 33 units strong. So that's where we're headed. Okay? The last field I want to discuss with you folks is the electric field between oppositely charged metal plates, yes? So you might want to hold off on filling in this diagram because it's going to change momentarily, okay? So let's say I first start off with neutral plates. These is like two metal plates, like these two books, like here and here, like that, like there. That's what we're looking at. Two metal plates. And over here I have a battery. Thank you. And what I'm going to do is connect this battery so that the positive tip of the battery that is so lacking electrons, it's positively charged, it's desperate for electrons, that's going to be attached to this one right here with a wire conductor where electrons can easily flow through. And then over here on the flat little side, this is like the knob, you know, this is the positive sign, and over here is the negative, that side's going to be connected right here, yes? Well, if this is super duper positive, remember these are real McCoy protons, they're locked up, they're not doing anything there, yes? Well, what would these electrons here end up doing? They're going to end up going through the wire to that positive side there, yes? And if they cruise over that way, of course not all of them, but enough of them, then what kind of charge is going to be left in that top plate? Positive, yes? So when you connect the positive terminal of the battery to that top plate, the electrons are attracted over there, and you have a positive top plate. Over here with this negative side, the flat side of the battery, you know, there's no knob there or anything, it's just kind of flat. There's all kinds of extra electrons, and they're so repelling each other. Repel, 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 yes? Well, guess what some of those electrons start to do? Yeah, they repel each other away from the battery, yes? And like here's neutral territory. So then they just kind of make that sucker negatively charged. So the top plate becomes positively charged and the bottom plate becomes negatively charged. If we map the field between here, folks, by pretending to place a tiny imaginary positive charge in there, yes? Which way would that positive charge move? From the positive to the negative, straight down. I placed it here. How would it go? Give me 30 seconds to wrap this up, folks. If I placed it here, how would it go? Straight down. If I placed it here, it would go straight down. Here, straight down. Now, notice the spacing between these lines. Since they're all going straight down, yes? Are they getting any closer together or farther apart as you go down? No. So what does that tell you about the strength of the field everywhere on the inside? It's the same strength. It's constant. It's called a uniform electric field. And that's the last answer to that packet. It's a uniform electric field. That's what makes it special. Ladies and gentlemen, I believe we have just completed lesson 3 and lesson 4. So tonight's homework is lesson 3 and lesson 4. Have a great weekend. So you have a uniform electric field. Same strength throughout. Since the lines are parallel. Not getting any closer together or any farther apart.